Earth. Low-tech special effects, guys. How we doing, 7th grade? We are going to be talking about the structure of Earth. You guys have worked on some stuff yesterday. We're going to do some other stuff. So hopefully that gave you a little chuckle. But we're going to talk about the structure of Earth today and the factors that make up the Earth. You did an assignment on it yesterday in the Ed Puzzle. So we're going to talk a little bit more and kind of conclude our week talking about the structure of Earth today. So let's take a brief look at that, if you don't mind. And we will examine how Earth and what makes up the Earth. Hopefully you have a very good idea about how this is all set up at this point. So when we look at the structure of Earth, guys, we're really looking at the inner workings of the Earth, kind of like, the bones of it, if you will, what makes Earth up. One of the little factoids for you, don't know if you know this or not, but one of the cool little things is the Greeks, back when we studied them, if you remember me in world history, they actually knew the size of the Earth. But it didn't get until the 20th century that they really figured out that the Earth has 3 primary layers. And you can kind of think of this like a boiled egg. You're going to look at it, the crust, the outermost layer, which is what we live on, is very thin. It's very rigid compared to the other two. Kind of like the shell of the egg. You crack it open. There's a bunch of that like egg yolk, white stuff, that gooey stuff, and then the yolk in the middle. But it can break, it can be fragile. It's what we call earthquakes and volcanic activity, things like that. All right. So there are 3 major parts to the structure of Earth. The first being the core. And I hope this doesn't get too confusing, but there's actually 2 parts to the core. The core can be broken down into 2 parts. And what you look at in there is the inner core. And this is hot iron. It's mixed with nickel. It's mixed with other metals. It is solid. Okay, it is just solid as a rock. Anyway, so I will not do that again. Anyway, but the inner core is a solid mass. And it is just, that's where you're spinning and all that. On the gravity, everything has made it solid. Now, if a little bit further out you get to the outer core. This is an area that surrounds the inner core, and it is so hot that all of the metals get melted. All right, so you have the gravitational force pushing down, but it's not as strong as it is the core. Thus, it can melt, and it's hot. All right, when we look at this, you're going to look at the second part then. That's the mantle. Now, the mantle is the biggest part of Earth. All right, that's what I want you to pick up on. It makes up 83% of Earth's volume. It's 1,800 miles thick. If you want to talk thickness, that's like getting in your car and driving like from here to Los Angeles. All right, it's that kind of trip. It's very thick. So when you look at it though, the mantle is also broken down into 2 parts because the area near the core is solid. It solidifies again. And then there's the outer mantle, and that is the melted area. We call that magma. I don't know if you guys ever saw any of the Austin Powers movie, but Dr. Evil loved saying that. He'd talk about the magma. But that's what you and I would call lava and stuff that comes out of volcanoes and stuff. So I hope this is weird enough to keep your attention. So the last part, and this is the part that we live on, is the crust. And the crust, compared to the rest of the Earth, wildly thin. This is why I talked to you about it being like an eggshell earlier. At its thickest, it's about 62 miles thick. At its thinnest, it's only about 31 miles thick. Think about driving like from here to Mount Vernon, and that's about as thick as it gets. And if you're wanting to say, like from here to, I don't know if this is a good example or not, but like say you get in a car and you drive from Shiloh over to say St. Charles, yeah, that's about as thin as it gets. So yeah, it's pretty thin. Especially when you consider that there's 1,800 miles of thick, hot magma underneath that. So we're just kind of floating on the magma. Woohoo! So it's all good. The crust is the thinnest on the ocean floor. and the Rift Valleys out in East Africa. We'll talk about the Great Rift Valley in Africa when we get to the African unit. But it gets real thin. So when you're going down in the ocean, just know this: the crust is getting thicker and thicker, or I'm sorry, thinner and thinner and thinner. If you go up to places where it's thickest, that means you're up in the mountains. That's where you're at. You're up in the Rocky Mountains. That's where the crust gets the thickest. Or up in the Himalayas, let's say you're climbing up Mount Everest or something, or you're up in the Alps. That's the thickest part of the crust. So I know that's common sense. That kind of makes sense, but that's just the best way to remember it. Really thick on the mountains, so up to 62 miles thick, and then really thin. You got to cut it in half when you get down to those ocean levels. So you get down to the Mariana Trench, which is the deepest part of the ocean. It gets down to about only 31 miles thick, and then it's a little interesting. So this is what we're actually looking at. This is kind of a good visual for you to look at the Earth's layers or the crust. And again, here's those three main parts. Remember the core, two parts. You've got the inner core and then the outer core. The mantle also breaks down. This area right here is still solid. So solid, melty, solid, and then melty again. And then up here, we're just on the crust chilling out, taking our road trips to the beach, tanning in the sun, or getting rained on, I don't know. But that is basically what makes up our Earth. And so this kind of gives you your three primary layers: core, mantle, and crust. Now, the parts of the crust that we're on are called tectonic plates. We'll talk a little bit about continental drift theory and whatnot. But these are the parts of the crust that technically float on top of that magma on the mantle. All right. Scientists believe that tectonic plates move around in all directions. There's no real rhyme or reason, but when they bang into each other, it can help cause volcanoes to erupt. It can cause earthquakes to occur. Tsunamis happen. I believe it's Alfred Wegener was the person that developed the plate tectonic theory. And so when you look at plate tectonic theory or continental drift, as it's better known, you want to remember continental drift. That is how we explain some of those things. Like I said, volcanoes, earthquakes, tsunamis. Okay, that's what it is plates are shifting. If they drop on the ocean floor, that'll help cause a tsunami. If they bang into each other, that's an earthquake. If there's more pressure coming up from the magma, that's a volcanic eruption. This is what we've got. We live right over here on this little like yellow dots and stuff, and you'll see that we get earthquakes. We live by what is called the New Madrid fault line. We have various variable volcanic earthquake activity out in this area, in the St. Louis area. They are always waiting for a big one to occur out this way. But you probably know this fault line a little bit more famous. It's called the San Andreas fault line. I used to live out this way in Los Angeles. And earthquakes happen a lot. So often that, frankly, if you talk to people in San Francisco or LA or San Diego or anything like that, we really don't notice earthquakes when they happen. So you'll notice them around St. Louis because they never occur. But frankly, out here, you're going to get them a lot in these areas. And so you'll experience some Seattle, Portland, all that. The West Coast is known for them. But you do get some activity out here as well. And that's because they believe that this, we call it the North Atlantic plate, that's the continental plate, that's the continent plus the oceans and everything, is stretching and it's banging into what we call the Pacific plate. And we don't know if it's really banging into it straight like this or if it's kind of rubbing up and down like that. Again, they kind of move in all sorts of directions. But this gives you an idea as to where all of the tectonic plates boundaries are. You probably have heard of like earthquakes and stuff down in like Haiti. There it is right there. They had a really big earthquake a couple years back. You see earthquakes and stuff all over down over here on the Andes Mountains in South America. It shouldn't surprise you then on these borders. I want you to see this relationship. There's a mountain on the border here. Here's the Rocky Mountains, right? Here's the Alps all the way up here. Here's the Kunlun Shan and the Tian Shan mountain range. You're getting into the Himalayas over here. You're looking at different forms. And so when these plates are banging into each other, it also helps create mountains. We'll talk a little bit more about that later. So how are landforms shaped? All right. Multiple ways. There's weathering. This is the process of breaking up surface rock, boulders, gravel, and sand. Weathering can happen just through exposure from a lot of sun, from a lot of rain, from just being exposed to the elements. Wind, things can look weathered. They can look a little beat up. Water, frost, chemicals, all of this, even plants. You'll see like a plant growing up through the road or a sidewalk or something. We would determine that as weathering, all right? And what that does is it's going to start to form some cracks and stuff. It's going to look a little beat up. Then there's erosion. Erosion is the process of wearing away and moving out the weathered material. Maybe you've seen some cracks or something form, and then there's like a massive rain and it washes out, and all of a sudden you see the cracks aren't just cracks anymore. Now they're kind of like potholes or things like that in the road. What that is water, wind, ice. Those are the biggest factors that actually help wear away surface material. It might rain, like say you're up in the mountains, water might get down into a crack overnight. It might freeze. That ice hardens, it expands, it starts to break more and more of the rock away. So you're going to see erosion or erosive activities like that. All right. So with that being said, we're going to stop right there. We'll talk a little bit more about erosion and weathering next week. I hope everybody is having a good week. Double check, make sure you're going into your Google Classroom, click that check your work, make sure that work is getting turned in, make sure you're not missing anything. Just so you know, we just got this, progress reports. Yeah, they're coming soon, guys, faster than you think. It's already September. Well, yeah, grades, everything's got to be due by September 15th. Woo! There it is. And then you will get your progress reports on September 17th. I know, that's way fast. So if you got any questions about that stuff, let's talk about it at the Zoom today, and I will see you then. Have a good one. Oh, and before I forget, we are going to have a quiz next week, okay? So be ready. I didn't give you a quiz this week, but you will have a quiz next week. We're going to post some new terms and stuff like, I don't know, weathering, erosion, stuff like that we've been talking about. All right, I will see you all on the flip. Hope to see you at the Zoom. Bye-bye.